Hello everybody. It is time for us to look at the 7-5 proportions in triangles worksheet. So finishing up topic 7 here. Going to look at the side splitter theorem and yet another angle bisector theorem. So first of all, it says what is Benson's error? Benson has used the proportion 5/10 equals x/7. The problem is that 5 and 10 are not corresponding in any way. They're not both on the same line, and they're not both the same segment of that line. So 5 and 10 cannot be in the same fraction of a proportion. That way, that's like the main reason that we can't solve this one. So one proportion we could use is 10/x equals 7/5, because we would be doing the line segments on the left over the line segments on the right, top over bottom, top over bottom. So we can say his proportion should be 10/x equals 7/5. And then when we solve that, x would be equal to 7.14. Number 13, what percent of the area of triangle PQR, the big one, is the area of triangle QRS, and explain. So what we see here is we see an angle bisector. So we can use our angle bisector theorem that tells us that the side over the piece of the long side, that bisected side, is equal to this side over the piece of the long side. So we can see how these pieces compare to one another. So I can say 8/6 equals 12/x. That's going to tell me how long RS is. So when I solve that, I get 72 equals 8x. Divide both sides by 8. 9 equals x. So I know x is equal to 9. So this is 9. And so when I find the area of these triangles, I notice that their bases are different, but their heights will be the same, right? Their height is not QS, but their height will still be the same. I can draw the segment from the top to the bottom that's at a right angle. That'll be the same height for both triangles. So what I can do is I can say the area of PQR, the big triangle, is equal to base times height over 2. That's 15, 6 plus 9, times height over 2. The area of triangle QRS is going to be the base of 9 times the height over 2. So then I can say that the ratio of the areas, let me draw a line here. The ratio of areas is effectively 9/15, because the height and the divided by 2 are the same for both areas. So if I compare 15 times height divided by 2 and 9 times height divided by 2, the area of QRS is 9/15 the area of PQR, which is equal to 60%. So the area of QRS is 60% the area of PQR. 17, 18, and 19 are about the side splitter theorem, and we just have to find appropriate measures, appropriate proportions to use. So if I'm trying to find the length of side X, I do know that I have a corresponding side to that. I have 13. And then I can pick any other pair of corresponding sides. Maybe I use the left side of this triangle using base X, and the left side of this triangle using base 13. So I can say x base side over 6 left side equals 13 base side over 6 plus 2 plus 4, 12 left side. And so then I cross multiply, I get 12x equals 78, divide by 12, and I get x equals 6.5. There you go. for 18 to find y, again, I'm trying to use pieces of this triangle that I already know and use the side splitter theorem. So y is corresponding to 2. And I also know that there's lots of other correspondence here. I could use this 4 and this 6 as well as this 2 and this y. That's one way I could do it. I could use this 6 and this 9 as well as the 2 and the y. So whichever way. So I'll go 2 over 6, the left side over the bottom left side, equals y over 9, the right side middle over the right side bottom. Cross multiply, 6y equals 18, divide both sides by 6, and I get y equals 3. All right. And then for z, I have the side right here. And I can do a proportion that's very similar to the proportion that I did in 17. I can say left side over base is equal to the entire left side of the triangle over the base of the entire triangle. So 4 over z is equal to the entire left side 12 over the entire bottom side 13. Cross multiply, I get 12z equals 4 times 13 is 52, like a deck of cards. Divide both sides by 12, and I get z equals 4.3 repeating. All right, next, got another side splitter. What is the value of x? So I'm looking to make proportions that will work here, and I can use the long side on top over the short side on top, 16 over x. Equal to the long side on the bottom over the short side on the bottom, x over 4. Then cross multiply, I get x squared equals 6 times 4, which is 64. Then I've got to take the square root of both sides, and I get x equals 8. So 8 is the value of x. Numbers 21 through 23, we are using the angle bisector theorem. If we have these given values of y, these are all going to be similar problems because we're just going to make proportions with that given number as the y value. So for 21, I could say 15 over 7 equals 16 over x. For 22, I could say 15 over 7 equals 20 over x. And then for 23, I could say 15 over 7 equals 18 over x. And then I could go through and cross multiply all of those. And for 21, I'm going to get x equals 7.46. So 7.5 rounded to the nearest tenth. For 22, I'm going to get x equals 9.3 if we're rounding to the nearest tenth. And for 23, I'm going to get x equals 8.4. All right. Number 24, write a proof of the triangle midsegment theorem. So the triangle midsegment theorem tells us that if DG is congruent to GE, so if we've split this side in half, and if EH is congruent to HF, so we've split this side in half, then that means two things. That means that GH is parallel to the base DF, and GH is half the length of DF. So I'm going to write a paragraph proof here, and I'm going to use triangle similarity to give myself this proof. So I'm going to start with given information. I can say since I know that DE is 2 of side GE, because DE is twice as long as GE, and FE on the other side is equal to 2 times HE, twice as long as HE. And I know an angle, right? I'm going for similarity. I know that angle E in the big triangle DEF is congruent to angle E in the small triangle GEH. That means I know that triangle DEF is similar to triangle GEH by side angle side similarity. Since these triangles are similar, and we know that the corresponding angles of similar triangles are congruent, we know that the other two angles of the triangles are congruent as well. So we can say since corresponding angles of similar triangles are congruent, then we can say angle EDF is congruent to angle EGH. And since EDF is congruent to EGH, then we can say that by the converse of the corresponding angles theorem, that means GH and DF have to be parallel to one another. So we can say, let's see, GH is parallel to DF by corresponding angles, because those corresponding angles are congruent. Corresponding angles. And we also know that the triangles are similar with scale factor 1/2, since we know that DE is congruent to 2GE. So DE is twice as long as GE. So we can say, since the triangles are congruent, the triangles are congruent with scale factor. With scale factor 1/2, that means, or 1/2 from, I guess we should say, which triangle to which triangle. So from triangle DEF to triangle GEH, then we know that GH is equal to 1/2 of DF, and we've proven both parts of our triangle midsegment theorem. Moving on, a building in the shape of a pyramid needs to have supports repaired, and two parallel sections need to be reinforced. The face of the building is an equilateral triangle. What are the lengths of KO and LN? So the face of this building is an equilateral triangle, and it's got parallel sections. So we know that these are parallel, even though it might not look exactly like that, but we're looking at this building not straight on, which is why our side lengths look a little strange here. So if we know that this is an equilateral triangle, and I know all of side JM is 30 units long, then that means JP must be 30 units long, and the base must be 30 units long. So if we want to find the length of KO, which is this medium segment, we can use the side splitter theorem. We can say that 18 plus 6, so 24, over this side is equal to the entire side length 30 over 30 here. So we can say that 24 over KO is equal to 30 along the side and 30 along the base, which of course means that KO equals 24. Okay? So then we want to find LN, and LN is another one where we're like, okay, there's LN right there. And I know that LN is going to be another piece of equilateral triangle. So if I did 18, that side length, over LN, that would be equal to 30 over 30 again, which makes LN equal to 18. So those are just smaller equilateral triangles that are similar to our large equilateral triangle. Number 28, Aisha is building a roof and needs to determine the lengths of CG and CF from the design shown. How can she determine CG and CF? What are CG and CF? So how can she do it? She can use the triangle angle bisector theorem, because that's what we've got going on here. So she can use the triangle angle bisector theorem. And she's trying to find the length of CG and CF, which are congruent. They're these lengths right here. So what we can do is we can use the triangles formed right here. Let's see, which ones would be good ones to use? Oh, we need some more pieces of information. We need to know how long these segments are. But that's easy because they're congruent. And we know the entire thing is 33 and the middle piece is 9 feet long. So we can do 33 minus 9, that's equal to 24. And then 24 divided by 2 equals 12. So AG is 12 and EF is 12. Then we can use the side splitter theorem. We'll call CG our x value. And we can say 12 over 10, not the side splitter, the angle bisector theorem. So this side piece over the bisected side is equal to this side piece, x, over the side opposite, which is 8, equals x over 8. And then we will cross multiply. We got 10x equals 12 times 8 is 96. Divide both sides by 10, and we get x equals 9.6. So CG equals CF, which equals 9.6 units, 9.6 feet. Okay. 29, what is the value of x? We can use our side splitter theorem a number of different ways here. We don't have to use full side lengths. We can pick x and 10, skip over this middle where we don't have any information, and then use 12 and 15. And that's totally fine. So if I'm taking my left sides, I can say 10 over 15 just fine. And on the right, I can say x over 12, and that's completely allowed. We don't need our side lengths to be right next to each other, or our segments to be right next to each other in order to use the side splitter theorem. So we've got 15x equals 120. Divide both sides by 15, and we get x equals 8. So the value of x is 8. And then number 30, what is the measure of side CB? Easy triangle angle bisector theorem. So here's our x. So we can say x over 4.2 is equal to 6.4 over 3. Again, just make sure that your proportion uses things in the right order. If I'm using an x here and a 4.2 on the opposite side, I need to use the other leg, 6.4, and then the 3 on the bisected side. And if I solve for x here, I end up getting x equals 8.96, and my answer is C. All right, let me know, of course, if you've got any questions on this material as we finish up Chapter 7.